we're gonna redo the fourth lecture because I think I can do better. Alright, so start over again. So we ended off in the previous stream, the third lecture, with talking about the creation axioms. Now, while I was mentioning the creation axioms, one of them, the union axiom, if you remember, I gave it as a preliminary form or like a weaker form, right? So it turns out that there's a stronger union axiom, a more powerful version of the union axiom, which is the one that we actually choose to use as an axiom, not the weaker one. And obviously, if we make it so that the stronger union is an axiom, if we set it as an axiom, then obviously that would imply that the weaker version is true as well, right? So it's the stronger one that we actually use as an axiom, but I introduced the weaker one first because, well, it's just to help build, just a little bit more intuition and understanding about how unions work before we delve into, the more complicated, stronger union axiom, which is more difficult to formulate and understand without understanding the the weaker form first. So that's why I introduced the weaker form first. Anyway, so let's just review what unions are, right? So the weak union axiom, I'm just gonna say WUA. It says that we can take two sets A and B, like two viable sets, and then we can construct their union A union B, and this will also be a viable set. So for example, if we know that the set containing 1 is viable and the set containing 2 and 3 is viable, then we can construct the union between the two sets. And obviously this will be equal to 1, 2, and 3. And that's basically how the union works. That's how we set it to function as. This is how unions behave, okay? And because this is how it behaves, we have the following, statement. If X is in A union B, then X is in A or X is in B. And this goes the other way around. So we also have if X is in A or X is in B, then it must be that X is in A union B, right? Because what we're doing here, right, is we're collecting all the elements inside of A and all the elements inside of B, and we're putting them all together in one set. So I take an element here, I take an element from set A, I take an element from set B, I take another element from set B. These are all the elements that are available for us to take. We plop them in to another set. That is how we construct the union, right? And so because of that, right, if something is in the union of A and B, then it must come from either A or B, because literally that's how we make the union. That is what the union is. The union is a collection of things from A and things from B. So if you take an object from a union, right, you take an element X from the union A, and between A and B, then it must come from either A or B. Similarly, if you take an object from either A or B, that means it must be in the union between A and B. Because to construct the union between A and B, you're either taking this guy and putting it into the set AUB, or you're taking something from B and you're putting it into the set AUB. Right. So let's do a little warm up here with a proof for the following statement. Right. For any set A, we have A union the empty set equals A. How do you prove such a thing? Well, we have to prove two things, right? That A is a subset of a union empty set, and also that a union empty set is a subset of A. Let's do the right one first. So we can play, the same game that I always use when we're proving these kinds of things, and that is Sal chooses an X from a union empty set, and Quan basically has to show that that X is an element of A. In other words, whatever Sal chooses, right? Sal can choose anything from here, and then Quan must be able to show that whatever Sal chooses is an element of A as well. So how does he do this? Well, we know that this is equivalent to X in A or X in empty set. So Quan is able to determine that there are two possibilities. What Sal chose either has to come from A or it has to come from the empty set. So here's the idea. Well, there's nothing in the empty set, so it's impossible for whatever Sal chose to be from the empty set. Right, we have two possibilities, we eliminated one of them, and that leaves X is in A, which is exactly what we wanted to show. Right, that's the win condition here. Quan needs to show that what Sal chose is in A. So Quan breaks it down into two possibilities, and he eliminates one of the possibilities, and the remaining possibility is that X is in A. So that's the sequence of arguments that we're following here, right? And we can do, let's do the other one. So that's this one done. The other one, we have, the same deal. Instead, we'll have Sal chooses something from A, right? And the end goal is to show that X is in a union empty set. But we know that if we can show that X is in A or X is in empty set, then this will be true, right? So Quan needs to show this is true, but instead he can simply just show that this is true, because if this is true, then automatically this would be true as well, because these statements, as you know, are equivalent, as I've shown in the introduction. So now what Quan has to do is he has to draw, some connection between here and here, right? From knowing that X is in A, Quan needs to show that either X is in A or that X is in the empty set. And this is just automatic, right? You have to show either one of these is true. And, well, so these are like two separate win conditions. Okay, in order to win, you need to show, either one of these, right? Just one of them, right? You can just ignore the other one. Over here, we'll just ignore this one, right? Because, well, we have X is in A, and just there we go, right? I have to show that, well, let's just framework it in an easier way. I have to show that either the ball is blue or the ball is green, and over here I have the ball is blue. So yeah, here I have shown that the ball is blue, right? I only need to show you that the ball is blue. I can just ignore the other condition, right? Because I just need to solve or show one condition and not the other. And yeah, that's it. It's as simple as that. And so this over here is true as well. And in general, this doesn't need to be the empty set. It can be any set at all. For example, I can just have B here, where B can be any set. And obviously this will also be true because you play the same game. I pick something from A, I have to show that it is either in A or in B. And well, I can just so it's asking us to prove one of two things, either X is in A or X is in B. We can just forget about the X is in B part, right? X in A or X in B. We have to show either one of these things. You can just forget about this one, right? Your boss gives you two things that you need to do, and you can pick either one of them to do. For the day, just pick this one. Why? Because, well, what Quan chose is from A. Not Quan. What Sal chose is from A, and you need to show that it is in A. That's just an automatic condition, right? It's just automatically solved. You don't need to do any additional steps there. So some proofs are just like that. It's just immediate or automatic, as I call it. Yeah. So that's the entire proof done, right? The union of between the empty set and any other set will have no effect, right? Because, well, it makes sense. You're adding nothing, right? You're taking the elements of A and you're putting them into a set. Where is the empty set's contribution? And well, it can't make a contribution because there's nothing inside of it. So it also makes sense that way as well. Right, so now that we have, a bit more intuition about how unions work, let's talk about the strong union axiom. So again, the weak union axiom, you have AB and you get A union B. How is the strong union axiom different? Well, the strong union axiom, SUA, it tells us that we can take one set, and this, I draw it on purpose. It's like a fancy version of A, and you'll understand why later. And it tells us that you can take one set, take a viable set, and you can construct the union of A, of fancy A. Right, so we call this the union of A and B, or A union B, or the union between A and B. Yeah, those are the ways you call it. Over here, it's just the union of A. Right? So you know which kind of union we're talking about. This, usually in writing, this is like a small u, and this is like a bigger u, taller, bigger u. So that's how you can differentiate it in like text and writing and stuff. So it tells us that we can take one set and construct another set from it, but what does this set contain? What does it actually do? Right, over here we know what it does. It groups the elements of A, groups the elements of B, puts them in one spot, and then, place all those things into a set. So you have a set containing all the elements of A and all the elements of B. What about this? Well, this set satisfies a certain condition. So the objects in the union of A, fancy A, are the ones which satisfy this certain condition, that there exists a set inside of the fancy A for which X is inside of that set. It's a bit difficult to digest. Hold on, let me take a drink. Alright, this is a bit difficult to digest, but we'll provide an example to make things clearer. Basically, the only objects inside of this set are the ones which satisfy this condition, right? So if an object satisfies this condition, it is going to be a part of this set, and if an object is a part of this set, then it has to satisfy this condition. That's why we have the double arrows here. So this statement determines what should be and what should not be inside this newly constructed set. It gives us the instructions. Actually, it just like gives us the instructions on how to construct this set, right? We just have to check whether the conditions are true. So let's see an example of that in action. Let's say we have, so yeah, the reason why we differentiate between fancy A and normal A is because, well, I want to differentiate between these two, right? Usually we draw the fancy letters if we're talking about sets that contain other sets, which really doesn't make sense because every object is a set. So of course, like, a non-empty set will have to contain a set. But like, for example, it's typical to write something like this, right? Fancy A is a set which contains other sets. So when we're talking about there exists a set A that is inside fancy A, then we're talking about like either this or this guy, right? The sets which are inside of the fancy set A. But in reality, well, every object is a set. So even if you have like, yeah. So even if we're talking about A is equal to this, for example, right? The number 1 is actually a set. Like I said, every object in mathematics can be described in terms of sets. We just don't normally think of it that way, but we will reach that point. So yeah, it is a bit weird. But yeah, I'm sure if you read enough or if you expose yourself to enough set theory, then this will become a bit more easy to understand. So how are we gonna determine? So let's say this is our example of fancy A, and we want to use the strong union axiom. We want to apply the strong union axiom here. What will this new set be? What will it contain? How do we determine that? How do we construct this set? Well, let's check, the objects which satisfy this condition over here. So let's, for example, test the number 1. Let's set x equals to 1 and see if this statement holds true, right? Let's set this equal to 1. So does there exist a set inside of fancy A that contains the number 1? Well, yeah, it's this set over here. Okay, so because this is true, that would mean that this is true as well. Because these two statements are equivalent, you prove one, you automatically prove the other. And since x is equal to 1, we know that 1 is inside this newly constructed set. And we can, repeat the same process for the numbers 2, right? If x is equal to 2, does there exist a set inside of fancy A that contains the number 2? Well, yeah, it's this set right here. This set is inside of capital A and it contains the number 2. So yes, 2 is inside. And the same thing for 3 as well. And turns out that these are the only 3 objects which satisfy this criteria. So union of A is the set containing 1, 2, and 3. And if you're I made it a bit too big. And if you're observant, then you'll notice that this is the same thing as saying, the set containing 1 union the set containing 2 and 3. And now we might want to ask, is it true in general for, any two sets? Let's say if fancy A is a set containing, A and B, right? That's why, fancy set, a fancy letter is usually denotes a set which contains other sets. So like, this is how like things would usually be written, right? It's weird to put something like C here, Although you can, there's nothing wrong with that. It's just that we use the fancy letters to show that it's a set that is on another hierarchy, like a higher hierarchy, because it's a set which contains other sets. Right. So in general, if a set contains two sets, this set contains two sets, will applying the strong union axiom result in, A union B? Will this be the result? And let's see, let's check the proof, right? All we have to do is to, do the thing, we have to prove that this is a subset of AUB and that the other way around, AUB is a subset of union of fancy A. All right, let's do this one first. Okay, so we'll have Sal here. Sal chooses an X in UA. Okay, and we know, right? We know that this is equivalent to this statement. So we can just directly transform it. It means that there exists a set inside of fancy A such that X is in that set. Now, what is fancy A? Well, fancy A is oh yeah, this will be weird. Well, so I'll just change this to be C and this to be C. Right. There exists a set inside of fancy A which is, equivalent to the set containing A and B, such that X is inside that set. So there really are only two options for C. There are two options here. Because C is a set that exists inside of this set right here. Wait, no. Yeah, wait, yeah. Wait, what am I saying? Okay, hold on. C is a set that exists and it is inside of this set right here. And since there are only two objects in this set, there are only two possibilities for C. Either C is equal to A or C is equal to B. Right? And so this statement here transforms into either X is in A or X is in B. Right? So the object C is either equal to A or equal to B, which means that X is either inside of A or inside of B. Okay. But we know that this is just the same thing as saying that X is in A union B. So Sal chooses an object in here, and we follow this line of argument to show that it is inside of A union B. And this is, this point proven. But to prove the other point, well, we can actually go the other way around. We can use the same sequence of arguments and move in the backwards direction. So let's erase all the arrows here because we're going to go bring them the other way around. So now Sal chooses an object inside A union B. And this means that it has to be, the object that Sal chooses has to be either in A or in B. And this is equivalent to this. Right? We can draw an arrow from here to here. And then we can also draw an arrow from here to here. Right? If X is in A or X is in B, that means there must, exist something inside of the set containing A and B for which X is inside of that set. Well, yeah, the backwards direction here is a bit harder to justify because some arguments can go backwards, whereas some arguments cannot go backwards. For example, X is in A means that X is in A union B. I think we proved this before earlier, right? I don't know, maybe it's already deleted. Yeah, it is. But if you if you play back, we'll have proven this. This, by the way, is just A is a subset of A union B, right? This is the same thing as that. It's a reformulation. Any object that's inside of A is also going to be inside of A union B. This is just a reformulation of that. So look for something that looks like this in the, oh god, didn't mean to bring that up in the video somewhere. Right, so that's a statement that can go from one way, but unfortunately the other way around does not work. Why? Well, X is in A union B is same as saying that X is in A or X is in B, and we need to show that X is in A. So there are two possibilities here. Either this is true or this is true, and we need to basically we need to eliminate one possibility in order for us to be able to obtain the other possibility, right? For example, if B is the empty set, which for example, if B is the empty set, then this is true, okay, because we can eliminate that possibility. No object can exist inside of the empty set. However, if B is any other set, then there is no guarantee that we can eliminate this possibility, right? It could be that B is non-empty, it could have objects inside of it, so having an object X to be inside of B is a possibility to consider, and you can't disregard it, right, without further evidence. And so there is no way to go from here to here without, further information, right? Because we need to eliminate one possibility, and we don't have the justification to do that. However, the other way around obviously makes more sense, right? I have this information, I need to show this information. Well, that's already automatic. I either have to show this or I have to show this, right? I have two jobs that I can choose from. I can eliminate this job. Let me just forget about this job. All right, I want to show this job. I want to show that this is true, and that's already immediate or already automatically true. So it's a bit harder to show why this works around backwards, but let's do our best. I'm gonna drink more. All right. Let's examine this. Let's try to turn this into a game again. There exists a set inside of A, the set containing A and B, such that that set contains X. So basically, what if Quan wants to show that this is true, then Quan has to show that right. As evidence, to show that this statement is true, Quan has to present an object inside of this set, and he has to then show that X is contained inside of that object. So Quan needs to present an object. Well, objects are just sets, but whatever. An object C such that C is in B and X is inside of C. So there exists a set C or an object C inside of this, and then blah 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 blah. It's just the same thing as Quan needing to present an object C such that blah 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 blah. Right? That's how we can, restructure this in terms of a game. So what are our initial conditions? What are our statements that we can work with to start from? It is that X is in A or X is in B. So these are two possibilities, right? So possibility one is that X is in A, and Quan needs to be able to win this game under this possibility. And also Quan needs to be able to win this game in case the other possibility happens, right? Because we want 100% win rate, right? There are two, well, this is like Sal's move, right? So Sal can either choose something from A or choose something from B, which is what, this means, right? If Sal chooses something from A union B, he's picking something either from A or from B. So this is Sal's choice here. And depending on Sal's choice, Quan needs to play this game, right, based on the different conditions that are preset by Sal. And he needs to win because we need 100% win rate. So we need to consider all cases. So Quan needs to present an object C that satisfies this condition. Well, over here, on this condition, Quan can just let C be A. He says the object A here, it satisfies the necessary conditions, and obviously A exists, right? So yeah, this is true, right? Because A is inside of this set, and also X is in A, because, well, what Sal chose is from A, so I'm just using this to justify that. So similarly, if we have this condition instead, if we are under this possibility, then we can just set C is equal to B. And Quan does win because he has successfully shown that there is an object. Obviously, B is an object that is inside of this set, and X is also inside of B. So this is true, and yeah, that is why the argument works in the backwards way as well. So that's this one done as well, and so we have this statement over here being true. Now, it is easy to convince yourself after this that if we have A is equal to A, B, C, then the union of that will be A union B union C, and so on, right? If you have this, if it's now a collection of 4 sets, then what we'll obtain is A union B union C union D, and so on and so on and so on. Right? It's not too hard to convince yourself that. You can try to prove it yourself. You can think about it for a while, but it does make sense and I'm not gonna try to explain it further because I don't want to run out of time here. Right, so there is one issue here, and it is that what's the point of the strong union axiom then? Because, like, the strong union axiom allows us to, if we have a set containing, a bunch of other sets, it allows us to string them together and take their union. However, the weak union axiom can do the exact same thing. If you have the 4 sets A, B, C, D, what you can do is apply the weak union axiom to these two, and you'll get A union B. Apply the weak union axiom to these two, you'll get A union B union C, right? But obviously, the brackets don't matter, and then you can apply the weak union axiom again, you get A union B union C union D. And yeah, so with the strong union axiom, you can accomplish the same thing that the weak union axiom does, and with the weak union axiom, you can accomplish the same thing as the strong union axiom does. So what's the point? Also, first of all, there is an additional step if you want to, like, perform this maneuver here with the strong union axiom. So first, you need to if you want to do this procedure here of stringing them into a union, a sequence, stringing them into like a union, what you have to do first is you have to take these individual sets and you need to place them all into a single set, right? That's something you need to do first, and then you take the union of this, and then it becomes the string of unions. But first, how do you go from here to here? Because in the weak union axiom, you don't need such a step, right? But in the strong union axiom, you must be able to put these guys into a single set first. How do we do that? Right? So what you can do actually is you take A and B, you use the pairing axiom, and then you obtain this guy. You take C and D, you use the pairing axiom, and then you get this guy. You take this guy and this guy, you pair them again, and then you get this guy. Right, this is not exactly this yet, but what you can do now is apply the strong union axiom. And this will give AB union CD, and this will be A, B, C, D. Right. So you need to first perform this step, and then you obtain this, and then you can take the union of this, and then get the string of unions. So that's just a little detail that is missed out that I have to explain there. So right. So the weak union axiom can take 4 things or any number of things and place them into a string of unions. The strong union axiom can do the same. Obviously, there's a lot more complication and details there because first you need to take all these groups of objects and place them all into a single set like this, into this form here, before you can apply the strong union axiom. But we've shown that as well as possible. So what's the point? Why is it stronger? Well, consider the case where fancy A is a set containing an infinite number of sets. Right? Then via our axioms, we can take the union of that and we could get an infinite union. Right? Can we do the same thing with the weak union axiom? Well, sure we can, but that would take forever. We can take A1 and A2, we can use the weak union axiom and combine them together like this, and we can have A3 over here. We can do that. We could get A1, UA2, UA3, and then we'll have to do it again and again and again and again, and just keep going on and on and on. However, there's a problem with that. It means that you have to apply the axiom an infinite number of times, which is a bit unconvincing, right? And like, I don't know, the philosophers or whatever, they don't like that. The thing is, this allows us to create an infinite union in one step, in one fell swoop. And that's more convincing, right? You go from here, this object, into this object, takes one step. Okay, that's convincing. Okay, everything makes sense, blah, blah, blah. You go from this object to this object. If you use the weak union axiom, that'll take an infinite number of steps, and that's less convincing to, the philosophers or whatever. It's just a matter of taste, really. But yeah, this is certainly better in this situation because it avoids, complications, and it avoids us having to deal with infinity, right? Sure, you can say that, like, applying an axiom an infinite number of times is safe to do. That's a claim that you can make. However, it's a claim that most people will fight against you for. So, sure, you can make things work that way, but it'll not convince a lot of people. This just convinces more people. It's just a matter of taste. I'm sure there is a system where axioms can be used an infinite number of times. Maybe there is a system of maths where that's possible, but not here. Not what we're studying. So yeah, that's it for now. Hopefully this was better than last time's explanation, and I'll see you next time.